Hi everyone, I'm Paul Drobny, a data scientist and AI resident at Epsiva. I've had the opportunity to work on machine learning projects in logistics, finance, and now recruiting, applying AI to solve real-world problems. In today's job market, recruiters face hundreds of applicants for each role, making it difficult to identify top talent. In this project, we'll apply AI to rank candidates by building a prediction system that measures fit more effectively. The client for this project is a talent sourcing and management company focused on finding candidates for tech companies. Currently, their process is semi-automatic. The initial list of candidates is gathered by searches based on keywords such as data analyst or aspiring human resources based on the role needing to be filled. However, their ranking and fit process is completely manual. Ideally, they would like to automate the rank and fit process as well as have the ability to re-rank candidates based on ideal candidates' information. We were given 3 goals by the client. Predict how fit the candidate is based on their available information, rank candidates based on a fitness score, and re-rank candidates when a candidate is starred or an ideal candidate. The data comes from the client's sourcing efforts in Excel format. Any field that could directly reveal personal details was removed, and each candidate was given a unique identifier. The attributes are ID, title, which resembles what someone may enter in their LinkedIn headline, location, and screening score between 0 and 100. The provided Excel file was read and copied into a data frame. Now that we have our data available, we can move forward with data wrangling. To start, we check for data completeness. With the isNull function, we see there are 4 null values for title, which will be addressed later. Using the dtypes function, the data types for each column are confirmed. The describe function generates a brief statistical summary of the numerical features. Since the dataset contains object type or categorical data, we will need to rerun the describe function, this time adding include object. From the count, we can see that title has 4 fewer entries than the other features, matching up with what we found with the isNull function earlier. The top title in the list is Data Analyst, and the top country is United States. Since we had null values, we need to view the data to determine how to address them. Filtering the data frame for isNull, we can see the 4 rows that have no title. Title is the most critical feature in this data set to determine candidate fitness, and without it, the other features are irrelevant. In this case, the best choice is to remove the rows with missing titles, which is done using the drop NA function. Next, we'll create a function to check for invalid titles that do not contain any alphanumeric characters, and add a column to label the rows with invalid entries. There are 17 entries that are invalid, 1 entry with a dash before the title, and 16 entries that only contain a dash. To address the invalid titles, we'll make a clean title function to replace any dashes that don't have a letter in front of it with a blank. This will clean the 1 valid title we have and strip out any remaining blank titles. Lastly, we'll convert all the titles to lowercase to avoid any issues with case sensitivity later on. With the data cleaned, we can move forward with exploratory data analysis. To visualize which roles appear most frequently in the titles, we can use a word cloud. First, all the titles are concatenated into 1 text file. We'll set the stop words to the default stop word set. This will ignore common words such as in, and, the. The most frequent roles appear larger, which in this case are data science, data scientist, data analyst, and machine learning. To see if there's any location preference, box plots are used to show the range of screening scores by country. With higher scores appearing throughout the world from North-South America to the EMEA region to New Zealand, there does not appear to be any location preference. To visualize where most of the candidates are located, a choropleth plot was used. A large majority of the candidates are in the United States, with over 1,000 candidates. All other candidates had less than 100 candidates. A log scale was used to show differentiation between the non-US countries, with India and the UK highlighted in teal, leading the rest of the pack. We evaluated multiple approaches for our solution to determine the best one based on customer resources and business need. First, we'll look at word embeddings and sentence embeddings as the basis to compare our list of candidates. We'll look at a learn-to-rank model where the system will compare and rank pairs of candidates based on a given top 5 list of candidates. We'll make a starred ranking system. Candidates will be compared to user-inputted or starred candidates. If no starred candidates are selected, the system will only compare to the inputted job title. We'll also look at prompt engineering using LLMs both locally and through an API. Prompts instead of coding are used to request the LLM to perform a task and to define the desired output. We'll first look at word embeddings. We'll look at TF-IDF, Word2Vec, GloVe, and fast text. All of these transform the words into numerical vectors. Words with similar meaning or context will be closer together. For each word embedding model, vectors were calculated for each word in the title and then averaged. Cosine similarity was then used to compare the similarity for each of the vector averages. All 4 methods suffered from the same limitations. By using the vector average, the context is lost and more verbose titles tend to be scored higher. Sentence embeddings work similarly to the word embeddings, but apply a single vector to the entire sentence. Meaning depends on surrounding words, and semantically similar sentences are close in a vector space. SentenceBERT was used to encode each title to a vector, and as with the word embeddings, cosine similarity was used to calculate each title compared to the highest score title. SentenceBERT ranked the titles based on similarity and context to the highest score title. The difference from using word embeddings is more pronounced in the lower scores for SentenceBERT, where word embeddings scored unrelated titles such as medical biller much higher than SentenceBERT. To build a learn-to-rank model, we can use the earlier SentenceBERT results to help teach the model. First, we'll convert the cosine similarity scores to a percentage. Then the top 5 candidate scores are adjusted to 100 to indicate which candidates are preferred. For our learn-to-rank model, we'll use the neural network-based ranking algorithm RankNet. The model scores each title for relevance and applies a sigmoid function to the probability that one title should rank higher than another. The training loop split the titles into 2 lists and shuffled through each pair for comparison. With the model trained, we can select a reference title and calculate the probability that the reference title is a better fit than the other candidates. RankNet shows similar titles have a score of 0.5 or a 50-50 probability that the reference title is higher, while less similar titles show a 99% chance of ranking lower than the reference. This could be useful in eliminating candidates, but it isn't really effective in distinguishing between similar candidates. Next, we'll create a starred candidate system, where we can rank the candidates based on their relevance to either a keyword search or to a short list of ideal candidates. In this example, we did a keyword search for data analyst. The system looked through all the titles and found titles with data analyst and put them at the top. In the next example, we entered a reference candidate ID. The system then picked titles most similar to the reference candidate title, based on SentenceBERT cosine similarity. For a lower code solution, we'll use LLMs, starting with LLMs that are installed locally. Instead of code, we can feed the LLM a prompt defining the task we want it to do. For example, you are an AI hiring assistant. Rank the top 5 job titles based on their similarity to the search term in descending order. 3 popular LLMs that were evaluated are Qwen, Llama, and Gemma. With Qwen, we were able to get a meaningful output showing the results in JSON format. With additional post-output processing, the results could be cleaned up to provide a more concise and comprehensible format. Additional prompt tuning would be needed to add candidate ID to the output. With Llama, the output was clean and concise, showing the top candidates by rank and title with similarity score, but it was unable to show the job ID. Additional prompt tuning would be needed to add candidate ID to the output. The output does include additional reasoning, which could be cleaned up post-output. For Gemma, the output at first glance appears to give the most desired result compared to the previous 2 LLMs, showing a top 5 list by rank, ID, and job title. However, after a quick cross-reference with the source data, shows the job titles not matching with the IDs. With these results being the closest to the desired output, we'll move forward with Gemma and work to improve the output. To address the ID title mismatch, we need to let the LLM know that the ID and title need to be paired together. First, we'll create a string that combines ID and title for candidate. Then, we'll update the prompt to look at the ID title pairs for each candidate. With the instruction updates, the IDs and titles of the top 5 candidates are now correctly paired. Next, we'll fine-tune the model to produce a cleaner and more consistent result. Clora is a fine-tuning technique that reduces memory usage by combining quantization, which compresses model weights to lower precision, with low-rank adaptation, or LoRa. This introduces small trainable matrices, enabling efficient fine-tuning of LLMs on less powerful hardware while maintaining performance. After configuring the model, the prompt is defined with explicit instructions on how the response should look, with an example of the desired results. Following training of the fine-tuned model, it is then merged with the pre-trained model from earlier. Following fine-tuning, we get the desired results, but there is a repeat of the prompt instructions prior to showing the results. After modifying the output to only show text following answer, we achieved the desired result of just showing our top 5 list. We now see the rank, candidate ID, and title for each of the top 5 candidates. If limited on computer resources, chatbot APIs provide a way to access higher parameter LLMs. Through Groq API, the Llama 3.1 8 billion instant and DeepSeek R1 Llama 70 billion were evaluated. Similar to local LLMs, a prompt is constructed to define the task we want done and to give an example of the desired outcome. The model is selected and the role of the chatbot is defined. In this case, Llama 3.1. After execution, results appear almost instantly. Although the format of the results look correct, we can see that the rank is not 1 through 5, and ID 332 appears 3 times. Next, we follow the same steps, this time switching the model to DeepSeek. Again, the results appear almost instantly, producing the desired results, this time without error. The improvement in performance is likely due to the higher parameter count of the DeepSeek LLM with 70 billion parameters compared to the previous Llama LLM with 8 billion parameters. In conclusion, sentence embeddings provide an effective way to compare job candidates with significant coding, can be used to develop customizable and scalable solutions as seen with the starred candidate system. Local LLMs provide private low-code solutions but come at the cost of high memory usage and slower inference speeds. For teams with sufficient resources or strict privacy needs, local deployment is a valuable path. LLMs accessed through APIs like Groq drastically reduce infrastructure overhead while delivering near instant inference and high quality results when prompts are well crafted. Ideal for when compute resources are limited. Data privacy, cost, and rate limits may raise concerns for enterprise-scale solutions. For more on this project, you can check out my article on Medium or the project repository on GitHub. And feel free to connect with me on LinkedIn by clicking on the links in the description below. Thank you for watching this video.